In this video, we're going to go over the answer, how we approach those type of problems. So we have, suppose that we have an object moving along a curve that, and the curve here is defined by RT equals 6t 5 sine 2t minus 5 cosine 2t. The first question is, give a vector valued function representing the tangent line to the curve given by RT at the point t equals pi over 2. So the key word here is tangent line. So there are two actually keywords here, tangent and line. Tangent line means that we're line, more specifically for a line we need a point on the line and we need a direction vector. Well, for the point of a line, it's easy because we want to know what's going on at pi over 2. So to find the point, the coordinates of the point at pi over 2, it suffices to use the vector value function that represents the curve because it gives you any points at any time t. So the first things I'm going to do is find a point by setting t equals pi over 2 and plugging into the vector valued function. So find r of pi over 2. So here if I plug in, 6 times pi over 2 is going to be 3 pi. 5 times sine of 2 pi over 2, 2 pi over 2 is pi, sine of pi is 0. And then we have minus cosine of 2t, which is going to be minus 5 cosine of 2 times pi over 2, which is cosine of pi. Cosine of pi is -1, but there's the -5 in the front, so the value is going to be 5. Hence, the point on the curve at t equals pi over 2 will have for coordinate 3 pi, 0, and 5. So I have a point. Now I need the direction vector. And this is going to be a direction vector to the tangent line. So that means that that vector is going to be tangent to the curve. And we know that at any point t, a vector that is tangent to the curve is going to be the derivative vector of r. So here we're going to find direction vector is going to be the derivative vector evaluated at pi over 2. So the first thing we do is find the first derivative of r. So which means here we take the r, which is 6t 5 sine 2t minus 5 cosine 2t, and we differentiate, meaning we differentiate each of its component. So we get 6. The derivative of sine t is a chain rule, where the inside function is 2t, the outside is sine. So you take a derivative of the outside function, the derivative of sine is cosine, keep the inside in, times the derivative of the inside, which is 2. And we do something similar for the other one, but remembering that the derivative of cosine is negative sine. So but there's a negative in front, so it's going to be positive sine of 2t times 2, right? And then we're going to evaluate it at pi over 2. So here, there's no t, so it's going to be 6. 5 times 2 is 10. 10 times, so this is 10. And cosine of 2t, when t is pi over 2, 2t is pi. Cosine of pi is -1. So it's going to be -10. And here, again, it's going to be 5 times 2 is 10, but sine of 2t is sine of 2 times pi over 2, and 2 times pi over 2 is pi, sine of pi is 0. So now we have everything. We have a direction vector of the tangent line. We have the point. The parametric equation will be then, remember, is x equals x0 plus at, y equals y0 plus bt, z equals z0 plus ct, when x0, y0, z0 are the coordinate of a point on the line, in that case 3 pi, 0, and 5, a, b, c are the direction number, which means the components of the direction vector, which are 6, minus 10, and 0. So if we do that, we get x equals 3 pi plus 60, y equals y0 is 0, minus 10t, and is going to be 5, and c is 0. So that's going to be the parametric equation. But notice here, I ask you to give a vector value representation. So instead, we're going to put this in vectored form, where the parametric equation are going to be the x, y, and z component of the vector value function that give the tangent line. So that is how we approach finding either the set of parametric equations to the tangent line, or if we put it into a vector valued form. The next question is find the unit tangent vector for the curve given by RT. So here we already did a lot of the work. We know a tangent vector. Remember the tangent vector? I said at any point on the curve, the vector derivative is going to be tangent to the curve. And we already done that, and we even evaluated here at pi over 2. I'm not going to use that. I'm going to use the direct, because here we are not given a time. But we want a unit tangent vector. So remember, this is the notation for the unit tangent vector at any time. Is defined by the derivative vector, and because it's unit, so that means we divide by its magnitude. And so I already did the work here. The r prime, so I'm just going to combine the 5 and the 2 here, is the vector 6, 10 cosine 2 pi, and 10 sine 2 pi over its magnitude, which is the square root of the sum of the square of the components. So we're going to square 6, we get 36. We're going to square 10 cosine 2t. Both the 10 and the cosine 2t get squared. So I get 100 cosine squared 2t. And then again, plus the square of the last component. I'm squaring 10 sine 2t, meaning I'm going to square both the 10, which is 100, and the sine 2t, which is sine squared 2t. And again, here we can recognize, especially be ready to recognize that whenever you see cosine squared, sine squared, remember of the Pythagorean identity, cosine squared plus sine squared is 1, but here we have 100. So this is really 100. So this is 136. So it's going to be 6 over square root of 136, 10 cosine 2t over the square root of 136, and then 10 times sine 2t over the square root of 136. Which you can simplify here a little bit, but that's really what the unit tangent vector at any time is going to be equals to, because this is so we can simplify 136 is 2 times 68, which is 4 times 34. So the square root of 136 is 2 square root of 34, which I cannot simplify because it's 17 times 2. So I can simplify this as the vector. So 6 over 2 is 3, radical 34, and 10 over 2 is 5. So it's after simplification. And yet we didn't ask at any point here, remember, find the unit tangent vector for the curve given by RT. It's at any time here. The last part of this question is to find if a particle that moves along the curve given by RT, so it's the same curve, at pi over 2 is that particle speeding up, slowing down, or neither? And we want to justify our answer. So to know if an object is speeding up, slowing down, or actually at a constant speed, what we need to do is investigate the tangential component of the acceleration. If the tangential component of acceleration is 0, that means that the acceleration is not acting in the line of motion, which means that the speed is going to be constant. If the tangential component, the tangential acceleration actually act in in the line of motion in the same direction, then that means that the acceleration is going to pull the velocity vector, and that means that, because remember the velocity points in the direction of motion, so if they are in the same direction, the particle is going to speed up. But if the acceleration, the tangential acceleration is acting against the line of motion, so in the opposite, what I mean by against, in the opposite direction, then that means that the speed is going to be decreasing. So we need to look at the tangential component of the acceleration and its sign. And remember, the tangential component of acceleration is computing by looking at the dot product of the acceleration with the velocity over the magnitude of the velocity. And again, you see that makes sense that if the tangential component is 0, that means the dot product is 0. So that means that the acceleration and the velocity are going to be, so here if it's 0, this is equivalent that A is perpendicular to V, which is equivalent to constant speed, because the acceleration is not acting at all in the direction of line of motion. If it's less than 0, that means that the angle between A and V is greater than 90 degrees. All right, so that means that the particle is going to slow down because the acceleration is pulling the other direction, basically. And then if it's greater than 0, that means the angle between the acceleration and the velocity is less than 90 degrees. That means that they cannot work together, so that means that the particle is going to speed up. So we're just going to find this. Well, we kind of already computed the velocity, because remember the velocity is the derivative of the position vector, and we already found it. It's right there, right here, when we did find the unit tangent vector. So here the velocity vector, we already have it. It's right over here. I don't need to make it of length 1, so I'm gonna just leave it as 6, 10 cosine 2t and 10 sine 2t. And then we want to find the acceleration. The acceleration is the derivative of the velocity. So I'm going to differentiate the velocity. So if I differentiate each component, I get 0. Again, this is a chain rule where the inside function is 2t, the outside is cosine, so I think I'm going to do it just very quickly here. It's going to be 10 times negative sine 2t times 2, so it's going to be negative 20 sine 2t. And similarly here, derivative of sine is cosine, the derivative of the inside is 2, so it's going to be 20 cosine 2t. And here we want to know what's going on at pi over 2, so I might as well just do it right there. So the acceleration at pi over 2, right? So we're going to look at pi over 2. The velocity is 6. When t is pi over 2, 2t is pi. Cosine of pi is -1. Sine of pi is 0. The acceleration similarly is going to be vector 0, 0, minus 20. So the tangential component is going to be the dot product of those two vectors. And really what I care is the sign, so I don't really need, I know the magnitude of the velocity is the speed is always positive. And remember we square each of the component and add them up, so we get 36 plus 100 plus 0. And if we do the dot product, we do the product of the x component, 6 times 0, -10 times 0, and then 0 times -20. Sorry, it's a little bit, sorry for that. It's a little bit messy. My 0 doesn't look like a 0. Over the square root of 136, but you see, this is 0. So AT is 0. So we have a constant speed. And we saw that because I noticed that the derivative of r prime, the magnitude of r prime, which is right there, was square root of 36. It was regardless of the time. It was always equals to 136. That means you have a constant speed. But if it's not constant speed, then to determine if an object is slowing down or speeding up, you don't have a choice. You look at what's going on with the sign of the tangential component of acceleration.